এবার দেখাচ্ছে নাকি? দেখো, দেখাচ্ছে তো। হ্যাঁ হ্যাঁ, ঠিক আছে। নাও, কিছু করতে হবে না। তুমি কানেকশন না চলে যায় কেটে দাও, তাহলে কিছু করতে হবে। এখানে স্পিকার লাগানো নেই, কানেক্ট করা নেই। স্পিকার কানেক্ট করা আছে এখানে। সুরেশকে ডাকতে হবে। হ্যাঁ স্যার, কানেক্ট করিয়ে দাও তো স্যার। সেটা তো আমি করতে পারবো না, সুরেশ। হ্যাঁ ডাকতে হবে, ডেকে নাও। কৌশিক, সুরেশকে একটু ডাকো। সকালেই করা উচিত ছিল। ওপেন আছে, ওপেন আছে, করে নিন। এখান থেকেও, এখান থেকেও প্রায় আমরা এখান থেকেও নেবো, আর এখান থেকে একটা নিয়ে নেবো। করেনি এখন। স্যার ওনাকে হোস্ট কন্ট্রোল দেওয়ার দরকার নেই, ওপেন তো না স্যার। ওনাকে তো হোস্ট কন্ট্রোল দেওয়ার দরকার নেই স্পিকার, ও তো ওপেন ফর অল, যে কেউ স্ক্রিন শেয়ার করতে পারে। ঠিক আছে। এটা কি কিসের কানেকশন এখানে? স্পিকার ম্যাডাম আছেন কি? কেউ একটু কিছু বলুন, যদি বলুন নিজে। এখানে অন শোনা যাচ্ছে নাকি স্পিকারের দিক থেকে?
হ্যালো। Hello. Good afternoon, everybody.
Good afternoon, madam.
Hello.
Hello.
কি কাণ্ড
Good afternoon, everybody. Now we want to start our today's FDP program. Oblasha, madam, can we start the program?
Okay, madam.
Okay, okay, madam. Thank you very
Good
much.
afternoon,
Please
everyone.
continue the program.
Okay.
Thank you. Okay,
Okay.
okay,
Thank you, madam. Good
okay. Most
afternoon,
welcome.
everyone. Welcome to day two of the Faculty Development Program on recent trends in renewable energy, organized by the International Quality Assurance Cell (IQAC) of Regent Education and Research Foundation group of institutions. I am Abhilasha Sao, Assistant Professor of Basic Science and Humanities Department, and is with me Mr. Sabyasachi Mukherjee, Assistant Professor of Mechanical Engineering Department. We are delighted to be your host for today's session. Attendance in all sessions is compulsory to qualify for the certification. Today, we are privileged to have with us a highly accomplished expert in the field of civil engineering, Dr. Amartya Kumar Bhattacharya sir. Dr. Bhattacharya is the chairman and managing director of Multispectra Consultants, Kolkata, and a retired professor of IIEST Shibpur, a chartered civil engineer. He is an alumnus of Jadavpur University and IIT Kharagpur, holding 3-year civil engineering degrees. Over a career span of 36 years, he has published numerous research papers, books, chapters, and has delivered keynote addresses at several national and international conferences. His area of expertise include fluid mechanics, hydraulics, hydrology, water resources engineering, environmental engineering, geotechnical engineering, and concrete technology. He has also been a member of the editorial board and a reviewer of several reputed journals. Today, Dr. Bhattacharya will share his insights on recent advancement in hydropower generation. We are eager to gain valuable knowledge from his expertise in this domain. Now, let us welcome Dr. A.K. Bhattacharya sir to take over the session. Sir, please.
Hello, sir. Sir, you are not audible, sir. স্যার তো জয়েন করেই আছেন কিন্তু
Hello. Sir, you are not audible.
Sir, you are not audible.
Hello, can you hear me now?
Yes, sir. You are audible, sir.
All right. So, um, as I was talking, there are different types of mm, energy, like thermal energy, hydroelectric energy, nuclear energy, solar energy. Now, out of these, only solar energy and hydro energy are renewable energies. So hydroelectric energy has a number of advantages. First of all, it does not produce any waste, no pollution. So it is a green technology. It is aligned towards sustainable development. It is virtually inexhaustible. The water that flows downstream can be reused again. It is therefore aligned towards a circular economy. Now, what is the disadvantage with thermal energy? First of all, in thermal energy, we burn a lot of coal, so that fly ash has to be disposed. That pollutes the environment. Then there is a lot of smoke that results in air pollution. Okay, so as I was telling, in thermal energy, the um, burnt coal that heats the water to form steam, and that steam is passed through steam turbines, and that generates the energy. So thermal energy is very common, but it utilizes fossil fuel. There is land and air pollution. because of the fly ash and also the smoke. So our fossil resources get used up. So all these problems are there. Now, regarding nuclear energy, we again use up our resources, and besides, mm, in times of war, for example, it might not be very safe because if the enemy bombs a nuclear power plant and it gets destroyed, then a lot of radioactive material can spread to the surroundings. Solar energy is renewable and inexhaustible. The basic principle is we use solar panels to generate the electricity, and that electricity is fed into a grid. Okay, so today our focus is on hydro electric power generation. So I'll start a Google Slides presentation, and right. So let's come to this. Right. So hydroelectric power generation principles and practice. So I'm, as you know, Dr. Amarkan Bhattacharya, Chairman and Managing Director of Madhespara Consultants, and this is the logo of Madhespara Consultants. So electricity can be generated by thermal power plants, hydroelectric plants, nuclear plants, solar plants, etc. So we are focusing on hydroelectricity. So hydroelectricity is green and renewable. Downstream water can be reused. There is no smoke, no environmental pollution. So these are just some of the positive aspects of hydroelectricity. On the negative side, if dams are constructed, then capital cost may be high. Operational costs may be low or medium in nature. Right. Just a minute.
Sir, your two speakers are working simultaneously, so the echo is getting started. You have to switch off one speaker, then only echo will stop, sir.
Okay. So, so no fuel is needed is aligned with circular economy and sustainable development. Now, load in an electric grid may be divided into a base load and peak load. Okay, so what is this? Because the load in an electric grid is never constant, it fluctuates. So depending on the demand, it fluctuates. And it may be divided into a base load and a peak load. So the base load is basically the minimum load. So that's constant. And the peak load is a fluctuating component of the load. This load occurs uh, when the demand for electricity is high. So power plants may be built to cater for both these types of loads. Conventional hydroelectric power generation envisages construction of a dam on a river. So this is the conventional a large hydroelectric project. So dams are storage structures and barrages on rivers like the Farakka barrage, then the Durgapur barrage, etc. These are diversion structures. A dams may be a multi-purpose. There is upstream water is flowing and it is being impounded by the dam, and a reservoir is created behind the dam. and there may be a lot of purpose when building this dam. One may be flood control. That is, a dam can be used to control floods. That is reservoir routing. Also, irrigation may be a purpose of the dam. Hydroelectric power generation may be one purpose of the dam. Drinking water supply, and of course, industrial usage. Now, this is just a diagram of what is happening. There's a reservoir behind the dam, and the water is stored, and head is created. The water is under pressure. The water flows through a penstock. Then we have a powerhouse, and we have a turbine. Water passes through the runner of the turbine to the tail race, and the rotor is set in a state of rotation, and the rotating shaft is connected to the armature of a generator, and that's how the power is generated. Now, since the dam stores water, there's a high head. Water under this high head flows to a turbine and sets the runner in a state of rotation. The rotating shaft of the runner is connected to the shaft of the armature of a generator, and electricity is generated, and water flows out through a draft tube. Draft tube is needed only in a reaction turbine. Other types of hydroelectricity generation may use low heads like run-up river plants and tidal power plants. These plants use low heads and typically use Kaplan turbines, which are axial flow reaction turbines that are used when the head is low. Now we come to types of dams. Dams may be of different types: gravity dams, arch dams, earth dams, rockfill dams. These are just some of the types of dams. Gravity dams are very common. This is just a photograph of a gravity dam. We can see that this dam is pretty massive, and is quite high also. It stores water. This is the downstream side of the dam, and we have another photograph of a gravity dam. This dam is also quite high, and we can see we are seeing from the downstream side, and we can see the spillway. Now on top of the spillway are the sluice gates. Now this type of spillway is called an Ogi spillway. There can be other types of spillways like chute spillway, etc. Okay, but Ogi spillways are normally used for gravity dams. This is another photograph of a dam constructed in a hilly area. Now, gravity dams resist the lateral force of water by means of their weight. These dams are massive. They need strong foundations. They resist the toppling tendency of the water in the reservoir, as well as the shear displacement tendency by virtue of their heavy body weight, strong foundations. So, what is this? What is happening is that since we have water stored on one side of the dam, this water has a tendency to topple the dam. that's a rotation due to the moment. The other one is the water has a tendency to push the dam mm, mm, downstream. There is a tendency towards translational motion. Now both these are have to be resisted. Now these are resisted by means of the heavy body weight and strong foundations. Now foundations need to be very strong, no faults or other weaknesses. So we need to ensure that, and a survey has to be constructed, in-depth survey, geological as well as of other types. Now, if we have a geological fault or any other type of weakness, then the site is not suitable for construction of a dam, particularly a gravity dam or an arch dam. So careful site investigation is needed. Now, the weight of the reservoir and the dam may contribute to seismicity. Now, the dam and the reservoir have a lot of weight. Now, that may contribute to seismicity. So, if the zone is already prone to seismicity, we need to look into that very carefully. Maybe we need to simply omit that site for construction of a dam. Also, when selecting a site, the stream flow should be sufficient to justify the construction. The nature of soil is also important. There must be minimal seepage loss from the reservoir. So, if the soil is too much permeable and there is seepage loss from the reservoir, that is not good. We want to have minimal seepage loss. And also, if there is too much siltation in the reservoir from the upstream stream flow and or from the size of the reservoir capacity will decrease. So, dredging will have to be done frequently, increasing the cost of operation. So, silting in the reservoir is undesirable. Now, silt can come into the reservoir from the upstream stream flow. Also, it may come from the banks of the reservoir. So, if there is a lot of vegetation on the banks of the reservoir, that is desirable because we want to minimize the siltation in the reservoir. Otherwise, we'll have to maintain that reservoir, and the operation and maintenance cost will be very high. Now, this is a photograph of an arch dam. This is another type of dam. Now, the crown of the arch is towards the reservoir, and these arch dams can be thinner than gravity dams, so they resist the load. This is another photo of an arch dam, and another photo of an arch dam. So the spillways are letting the water flow out. So the sluice gates are open and water is flowing out over the spillways. So arch dams are arch-shaped. They transmit a part of their load to the foundation and a part of their load to the side abutments by arch action. So the gravity dams transmit their entire load to the foundation, whereas arch dams transmit a part of their load to the foundation and a part of their load to the side abutments by arch action. So load is transmitted both horizontally as well as vertically. So arch dams may be thinner than gravity dams because the load transfer is more efficient. Now the side abutments must be very strong to take the load transmitted by arch action. If side abutments yield, it may be disastrous. So we are doing the calculations assuming that the side abutments are strong enough to take the load transmitted by arch action. Now, if the side abutments yield, uh, then um, all our calculations will be wrong, and the dam may even fail. Now, this is a photograph of an earth dam. This is another type of dam, and this is constructed of earth. Now, earth dams are constructed with soil. They may be constructed on relatively weaker foundations. So that is the main benefit. Uh, we may construct the earth dams on relatively weaker foundations. Now, earth dams may be uniform in their composition or non-uniform in their composition. So, uniform in their composition means only one type of soil is used for the construction of the entire earth dam, and non-uniform means that mm, we may have, say, um, a relatively uh, more impervious core or an impervious upstream blanket, things like that, or a combination of both perhaps. So seepage through an earth dam, thus through the body of the earth dam, is a major issue. To reduce seepage, a relatively impervious core or an upstream blanket may be used. A rock toe may be provided to drain out the water which has seeped through the body of the dam. Now, another type of dam are rockfill dams. So, rockfill dams may have an impervious front face backed up by rockfill. The rocks may be dumped behind the impervious front face. So, this is one type of rockfill dam. Or there may be an impervious core with rockfill on both sides, that is on the upstream side as well as on the downstream side. Now, foundation requirements for rockfill dams are not as rigorous as for gravel dams. So, this is another advantage. Also, both earth dams as well as rockfill dams can often be constructed with locally available materials. So, this is one type of a rockfill dam having a core and different types of rockfill on both sides, upstream side as well as downstream side. Now, among other types of dams, we will mention buttress dams. These are not very common. This type of dam may have a front face that is on the reservoir side, supported by buttresses. So this is one diagram, or rather one photograph. As you can see, the face of the dam is on the reservoir side, and the buttresses supporting the face are on the downstream side. Now, in any hydroelectric power project, we have not only hydraulic structures but also hydraulic machines. So, water has to flow through turbines. So, there may be different types of turbines. Pelton, Francis, and Kaplan turbines are commonly used in different head ranges. Now, Pelton turbines are tangential flow impulse turbines and are used at high speeds. Francis turbines are radial flow reaction turbines and are used at uh, medium heads. Pelton turbines are used at high heads, sorry. Now, this is a single jet Pelton turbine. As you can see, water comes through the penstock and passes through a nozzle that flows into the air. A jet of water at a very high velocity is passing through the air at atmospheric pressure. It is striking the bucket of this Pelton wheel, and one bucket moves, the next bucket comes in its place, and the entire Pelton wheel is set in a state of rotation. So this runner rotates this shaft, and the shaft is connected to the armature of a generator. Now, then the water flows to the tail race. Now, this casing doesn't have any hydraulic purpose as such. It is simply used to prevent the water from spilling out. This is another pattern wheel which has jets, which has two jets. Now, Kaplan turbines are axial flow reaction turbines and are used at low heads. They are a type of propeller turbine with a blade angle adjustable. That is, for Kaplan turbines, the angle that the blade makes to the hub, that is adjustable. So Pelton turbines are best when heads are more than 300 meter. Francis turbines are best for heads between 60 meter and 200 meter. And Kaplan turbines are best for heads less than 60 meter. So this is a diagram of a Francis turbine. Water comes in from the penstock, then passes through the spiral casing, and then passes through the guide vanes. So these guide vanes regulate the angle with which the water enters the runner, then passes to the vanes, and the runners are set in a state of rotation, and then the water passes out. Now, this is again a diagram of a Francis turbine, and this is again another diagram of a Francis turbine. The shaft is vertical. After passing through the runner, water flows into the draft tube. So, impulse turbines like Pelton and reaction turbines like Francis and Kaplan have some differences. Impulse turbines have a water jet strike the impeller at atmospheric pressure. Water is done by the velocity of water only because the pressure is atmospheric, and the water falls freely after striking the buckets of the impeller. In impulse turbines, the downstream pressure is atmospheric. The casing of the turbine has no hydraulic purpose, and it is simply there to prevent the water from spilling out. A draft tube is not necessary. In a reaction turbine, the velocity and pressure of the water both do work. The downstream pressure is not atmospheric. A draft tube is needed. Water passes through the vanes of the runner. The casing is filled with water. So the principle of an impulse turbine and the principle of a reaction turbine are totally different. This is a diagram of a Kaplan turbine. The axis is vertical. So we have the spiral casing. So water is passing from the spiral casing and passing through the propeller blades. Now, when the water is passing through the propeller blades, the velocity and the pressure of the water are both doing work. The propeller is set in a state of rotation, and then the water is passing through a draft tube. Now, this is another diagram of a Kaplan turbine. Again, the same principle. So, this over here, this is again a Kaplan turbine. Here there are four blades of the propeller. So, there is no such fixed thing. The number of blades may vary, but here there are four blades. Now, barrages, canal walls, and other structures that create low heads can use these low heads to generate small amounts of power. So these are not very common, these are not very widely used, um, but these should be used uh, to much more, in fact, because where we have barrages and cannon falls and such structures that create low heads, um, we can put in small Kaplan turbines and generate a small amount of electricity, perhaps. In hilly terrain, small drops in stream elevation, such as when a U-loop in plan is accompanied by a large change in elevation, may be used to generate small quantity of power. Now, this was done in a tea garden in northern Bengal, where within the boundary of the tea garden, there was a stream that made a U-loop in plan, but that U-loop in plan was accompanied by a large change in elevation, and that was used to generate a small amount of power. Now, tidal power plants aim at creating enclosed spaces of water in tidal areas. Construction of barriers is needed. During high tide, gates are opened and water flows in and fills up. This water is let out through turbines during low tides when there's a difference in level of the water on both sides of the barrier. Generation of power by tidal power plants is intermittent. So tidal power plants are not very common. And this a study was done on whether we may have tidal power plants in the Sundarbans, but no execution was done. So basically, we create enclosed space of water in tidal areas using barriers. Now, we let the water flow in during the high tide, so the water uh, um, gets filled up to the high tide level, and the turbine gates are kept closed when the water is filled up. During low tides, when water is released through the turbine gates, because outside the water is at a low tide level, inside the water is at a high tide level. So that difference of water level is used. The water is let out through the turbine gates. Water flows out through the turbines, and a small quantity of electricity is generated. But the generation of power by these tidal power plants is intermittent, because always electricity is not generated. Electricity is generated only during low tides. So this is just a picture of that. So, but hydroelectric power needs to be generated more extensively. For example, the major part of the power generated by the Damodar Valley Corporation is generated by thermal power plants. Now, projects involving large dams tend to have large gestation periods and high capital costs. Now, this is one minus factor uh, mm, uh, in the construction of large dams. That is, they have large gestation periods and high capital costs. So this is just one photograph of a big dam structure on a river. This is yet another photograph. And finally, thank you. So
Thank you so
I
much,
guess
sir. It was Yes, sir. It was a wonderful session. So
that
now it's time for a question answer session. So anyone having any question, Sad is here. You can ask.
we have been discussing about um, hydroelectricity, and we have more or less touched on the basic factors like um, sites and hydraulic structures, hydraulic machines, different types of hydraulic structures, different types of hydraulic machines, low head, including tidal. And we started with mm, hydraulic advantages of hydroelectricity vis-a-vis other types of electricity generation.
Sir, there is a question among the
So,
participants. Um, he asked, have some discussion regarding Vortesk and other low head turbines.
all right. So, I think that's what I had to say as far as this hydroelectric power generation is concerned. Now, if you have any questions, you can ask me now.
Sir, Mr. Rovik Sharkar from audience has asked that please discuss about Vortesk and other low head turbines.
One thing that I'd like to say is that hydraulic energy needs to be used much more extensively than it is being done so far, because the Damodar Valley Corporation, with the number of dams, is still generating the major portion of its electricity um, by from thermal power plants.
Sir, am I audible? Can you hear me, sir? Is there any question?
So the I have intentionally not gone too much into the mathematical aspect, um, because if I went into the mathematical aspect like of equations, etc., then it would have been extremely lengthy. We can get into detailed calculations of, for example, hydraulic machines and um, um, get into calculations of power generated, power related to head, related to inlet velocity of water and such things. So I think there are books covering uh, all these things. Now, one aspect which I may talk about is mm, powerhouse construction. Powerhouse is normally constructed pretty close to a dam, but it may also be constructed um, uh, relatively far away from a dam. In arch spillways, arch dams, for example, sometimes spillways are constructed not close to the dam, but a little far away from the dam, and um, on they are chute spillways, for example, and we have mm, chute spillways constructed on nearby hills, etc., to let out water from the reservoir to, say, a surrounding stream. And it is not necessary that the chute spillway be constructed just um, close to the dam. So at the lower end of the chute spillway, we can have a powerhouse. We can have any type of turbine that we desire. It may be Pelton or Francis, depending on the head, and generate some power. Now, among other types of spillways, we may mention um, ski jump spillways. So these spillways have mm, these are ogee spillways having a ski jump at the bottom, so water shoots up at the tail end of the spillway. Normally, for a spillway, the dissipation of energy at the lower end is a problem, and we can have different types of energy dissipation mechanisms. Like we can have solid roller buckets, then slotted roller buckets, also ski jump may be there. So all these dissipate the energy at the lower end of a spillway. We can also have a spillway of the nature of a pipe, so that can also be there. So if you have any questions, you can ask me now.
Sir, am I audible to you, sir? Hello. I think your speaker is off, sir. Kindly increase your volume. I think you are not audible. Some questions is there in chat box. Are you audible, sir?
So we can have a detailed analysis of the hydraulic structures also. There is detailed calculations can be there. Nowadays, finite elements are mostly used. We can do detailed calculations for um, mm, gravity dams, arch dams, etc. So, in now before the onset of the finite element era, we used to do a different method for calculation of the load distribution for arch dams. So that method was mm, we what engineers used to do at that time was they split up this arch dam into vertical cantilevers and horizontal arches and assumed a certain division of load um, uh, between the arches and the there is a they assumed a certain distribution of the load um, um, between the arch action and the cantilever action. So with that, they found out they did the calculation and they found out the deflection by uh, of the by the from the arch point of view as well as from the cantilever point of view. Now, if these two deflections did not match, then it meant that the assumed distribution of the load between the arch and the cantilever actions was incorrect. So another attempt was made with a different distribution and another trial was made. Now, supposing the displacement did not match again, meant this assumed distribution was again incorrect. Then another trial was made until the deflections matched. So when the deflections matched, it was assumed that the distribution of load between arch and cantilever was okay. So this was the method that was used before the current finite element era. So a very famous arch dam would be the Hoover Dam. Now, regarding seepage under a dam, for gravity dams and arch dams, these are mostly constructed in rock areas, and there may be seepage through the foundations, although it is not very much normally. For earth dams, there is seepage to the body of the dam, and that is a problem. And it is undesirable, but it cannot be prevented entirely. To minimize that seepage, we provide a relatively more impervious core, or we provide an upstream blanket, so or we provide combination of these. So there can be different such techniques to reduce the seepage through the body of the dam. Rockfill dams are not very common, but they are relatively cheap. They can often be made with locally available material. Buttress dams are also not very common. Normally, gravity dams and arch dams also, these are very common, I guess. Now, design of hydraulic structures, this is also something that is pretty specialized. One thing that we are advocating a great deal is um, greater use of runoff river plants and other low-head um, hydro development scenarios to generate a small quantity of electricity. So it may look that these electricity amounts which are generated are pretty small, but they may add up to be pretty considerable. Um, so that is also something that needs to be looked into. And I think um, it's a pity that say Damodar Valley Corporation, they really have a scenario where they have a number of dams and they can generate a larger amount of electricity uh, via this tidal route, but still the overwhelming major portion of their electricity generation is through the thermal power plants. So I think hydroelectricity needs to be generated mm, in a much greater way. Also, I think I talked about multi-purpose dams. And dams um, can also be used in another way. More recently, this has come to light. Say, if you have a transboundary river, say like the Chenab River between India and Pakistan, and you have a dam in India, then if you want to say punish Pakistan um, mm, for sponsoring terrorism, then you can alternately mm, lower the sluice gates so that the Chenab is dry in Pakistan, then raise the sluice gates so that there is flooding in Pakistan. You can do this alternately. So that is in the hands of the upstream country. So if you want to punish an enemy downstream country, you can also do that if you have constructed a dam. So as far as hydroelectricity is concerned, I think that's about all. In India, hydroelectricity is generated to quite an extent, but could be generated more. Now, if you have questions, then you can ask me now.
Am I audible, sir? Hello. Hello, sir. I think your speaker is off. Am I audible? Hello, sir. Are you audible? Can you hear me? If anyone having any question, please write down in the chat box.
Okay, now if you are looking for um, good reference books um, for teaching students, then mm, for hydraulic structures, uh, rather hydraulic machines, a good book would be by K. Subramania, Fluid Mechanics and Fluid Machines. So there are lots of worked out problems on all these things. Um, all the three types of turbines, Pelton turbines, Francis turbines, and Kaplan turbines are covered. And there are a number of worked out problems, and they would suffice for all your classroom requirements. Now, uh, it is not desirable to increase the number of jets in a Pelton turbine because the efficiency of a Pelton turbine decreases as the number of jets is increased. So the most efficient Pelton turbines are those with only one jet. If you have two jets, then the efficiency decreases. If you have more jets, then the efficiency decreases still more. So it is not desirable to increase the number of jets of a Pelton turbine uh, very much. Now, one jet Pelton turbine is best. At most, you can go for two jet Pelton turbines, but don't go in for more than that. For um, Kaplan turbines, I think the optimum number of propellers, uh, rather the optimum number of propeller blades would be 4. For Francis turbines, it is variable. You can have a large number of vanes. So these are the three types of turbines which are used very extensively, and other than these three types of turbines, I don't think mm, other types of turbines are really used to any significant extent. So the basic topics that you need to keep in mind when studying this hydroelectricity uh, and also teaching this hydroelectricity are the pluses and minuses of hydroelectricity vis-a-vis other types of electricity generation. Then a selection of a site. Okay, types of hydroelectric projects. Then selection of a site for a dam. Types of dams, their pluses and minuses. Then types of turbines, their characteristics. Then low head hydroelectric projects, including runoff river plants and tidal plants. More or less, if you cover these things, then you would have covered the whole of hydroelectric power generation. You can expand on all these things by adding mathematics to all of this. Yes, if you have any questions, you can ask me.
I guess there is some problem at that end. Sir, I am audible. Can you hear me? Hello, Mr. Bhattacharya, sir. Can you hear us? Hello. I think there is some technical issues at their end. So we are going to conclude the today's session. Thank you very much, sir, for this session. As we conclude today's insightful session, we extend our sincere gratitude to Dr. Amartya Kumar Bhattacharya, sir, for sharing his valuable knowledge on the advancement of hydropower generation. We truly appreciate your time and effort in enlightening us with such valuable insights. And a heartfelt thank you all the participants for their active engagement, and we look forward to seeing you tomorrow on 15th of May 2025 at day 3 of the FDP. The session will be conducted online and will feature the expert talk by Dr. Shantanu Datta on exploring solar energy, state-of-art technologies, real-world applications, and research trajectories from 2:30 p.m. online. A feedback link will be shared in WhatsApp group like yesterday, and filling up the uh, form is mandatory for the certification. So thank you all and have a wonderful evening ahead. Goodbye.
Thank you, everyone.
Thank you very much, sir. The certificate of appreciation is now being shown to the screen. Thank you, sir, for sharing your valuable insights with us. And the certificate of appreciation of Dr. Amartya Bhattacharya, sir, is now being shown on the screen. And a feedback link has been shared. Kindly fill up the feedback link as well. Thank you so much, everyone, for joining with us. And we'll resume our 5 days FDP program tomorrow at 2:30 p.m. in Google Meet. Thank you, everyone.